Hello, I'm Justin Howard, and I'll be presenting a project on predicting data analytics submissions at WGU. The goal of this data analysis is to build a model that helps predict daily counts of student work submissions to the data analytics program at Western Governors University to help guide human resource decisions. The data in question consists of the time of each submission in year, date, month, hour, minute, second format. Also attached to that is student IDs, task IDs, and a binary pass-fail indicator. Looking at the realization of daily counts of submissions to the program reveals possible evidence of non-stationarity. A positive trend is likely given the growth of the program overall since its inception. Looking at the system frequency of the realization, a dominant system frequency of 0.0027, indicated by the peak I'm pointing to, is present. The second most dominant system frequency is 0. The third and fourth are 0.14 and 0.28. Three of those dominant system frequencies indicate a daily pattern. 0.0027 is equivalent to 1 in 364. 0.14 is 1 in 7. 0.28 is 2 in 7. All of those correlating to daily frequencies. Looking at the autocorrelation structure provides further evidence of a dominant daily trend. Peaks are occurring at every 7th lag, providing more evidence that a daily seasonal model is appropriate. So a year in this case will be defined as 364 days. Performing a transformation on the original realization reveals the second most dominant system frequency's wandering behavior. Maximum likelihood estimates will be used to identify the model best equipped to predict the transformed data. Also, due to the fact that there's a large variance in the series, coefficient estimates that are derived from both the original realization and a log transformed realization will be compared for forecasting. After the comparison was made between the estimates of the log transformed data and the raw data, the log transformed estimates were more likely to produce a useful model. So from that data, an ARUMA 2102 model with a daily seasonal pattern was created, and it had a white noise variance of 54.57. The residuals of this estimate appear to be white noise. The results of running 5 AIC estimates on the residuals provides an estimated phi and theta of 0, providing further evidence that the residuals are indeed white noise. It was previously noted that phi estimates based on the raw data and the log transformed data would be compared. During that comparison, it was noted that the system frequency of 0 is caused by a root near the unit circle. Upon examining the estimates from both the log and raw data, we see an actual 1 minus b component in both of them. And this is evidence to indicate that the underlying realization after accounting for the daily seasonal pattern could be a non-stationary process. However, for the purpose of this analysis, a 1 minus b non-stationary component is not going to be considered. Using that assumed stationary process, a 31-day forecast was generated. The ASE of this model turned out to be 74.84, and the RMSE turned out to be 8.65. During the multivariate analysis, 3 features were engineered from the daily counts of submissions. One was student counts, another was a count of failures or failed submissions, and a third variable was a count of the number of tasks. A full description of how each feature was engineered based on the daily counts is available on request. A cross-correlation analysis was conducted on the 3 engineered variables. 2 detrending transformations were conducted, one to remove the daily pattern that was already noted, and another to take out the first difference. Daily submission counts were found to be negatively correlated at lag 0 with all 3 engineered variables, and positively correlated at lag 1. Conclusions from this can be that submissions to the queue are predictors of fail counts, number of students actively contributing submissions, and the total number of tasks worked on. These variables are engineered from the submission counts to the queue and therefore may not be the most helpful in making predictions. A vector autoregressive model was tested with a 364-day seasonal pattern and a logical indicator for the presence of trend. Significant lags were at 1, 7, 14, 21, and 28. The vector autoregressive model with the lowest average squared error turned out to be that of lag 14. Still, even the best vector autoregressive model was not beating the simple univariate model. What we can conclude from that is that the three engineered variables being derived from the response variable are not useful predictors of the response variable. Two neural network models were also trained. The first one was a multi-layer perceptron model. The MLP forecast was not as good as either the vector autoregressive forecast or the ARUMA forecast. The second neural network trained was a long short-term memory recurrent neural network. For validation purposes, a rolling sample origin plan featuring 6 samples, all located near the end of the series where it was created. A more limited training set of 750 observations was created in order to permit the 6 rolling origin samples. The model was tested on 6 sets of 124 observations. The data was pre-processed, it was scaled and centered before used in the model. This is a visualization of the rolling origin sample plan. As we can see, the test sets were all located near the end of the series. The LSTM predictions were very poor. Our conclusions here are that more research into appropriate hyperparameter tuning and data pre-processing is needed. Final conclusion are that the parametric model outperformed a multi-layer perceptron and a long short-term memory neural network model. To deploy this predictive model, it is suggested that a prototype be built within the R-Shiny application environment. And for ideas on further developing this project, feel free to reach out to me at any time.